Buckling analysis is a key topic in civil and mechanical engineering used to find the critical load of a structure. Hello, I'm Armin. Before we begin, let me briefly explain the model. Let's get started. Buckling is the sudden loss of stability of a structural member subjected to compressive load, resulting in large lateral deformations at a critical value known as the buckling load. When a structure reaches this critical axial load, it no longer remains straight but abruptly deflects laterally, bending in a manner similar to a beam. This lateral deflection induced by axial compression is referred to as buckling and may lead to catastrophic failure, often occurring at stress levels below the material's yield strength. Assume a beam that displaces only in the y direction and is fixed at the bottom. The critical load and lateral deflection are calculated using the following formulas. Buckling can occur in plane or out of plane, and it depends on the value of the moment of inertia. If the cross-section is symmetric, the critical load is identical in both directions. I model a 1-meter beam with a circular tube cross-section using a 1D beam element in the static structural system. The top of the beam is restrained in the x direction, and the bottom is fixed. A -1 Newton force is applied at the top of the beam. After that, I use the Eigenvalue Buckling system to find the critical load. Here is a comparison of the analytical and simulation results for structural steel. The error is about 1.4%, which is acceptable. This explanation is sufficient. Let's get started with the modeling. For buckling analysis, we need two analysis systems, static structural and eigenvalue buckling. The eigenvalue buckling system is only a solver, and no boundary conditions are defined in this system. Therefore, the geometry, material, and all boundary conditions must be defined in the static structural analysis. I will start by creating the geometry. I right-click on Geometry and select New Space Claim Geometry. Before sketching, I change the work plane. I click on New Sketch Plane, select the XY plane, and switch to Plan View. I want to create a 1-meter-long beam. From the Sketch tab, I select Line, click on the origin, type 1000, and press Enter. I only need a line, so I click End Sketch Editing. Now the line appears in the Curves folder in the Structure tree. Next, we need to assign a cross-section to this line. I click on Prepare, and under Beam Sections, I find the Beam Profiles. I select the line, expand the profiles, and choose Circular Tube. As you can see, the line is now converted into a circular beam. I right-click on the circular tube and select Edit Beam Profile. Here, the inner radius is 10 mm and the outer radius is 20 mm. These values can be modified, but I will keep them unchanged. I press Escape and close the Beam Profile editor. Everything looks correct, so I close Space Claim. Next, I double-click on the Model cell to define the model and boundary conditions. We are now in ANSYS Mechanical. I expand the Geometry branch to check the material. As you can see, structural steel is assigned by default. You can change the material using the filter, but I leave it unchanged. We can also see the beam cross-section under the Cross-section node. Moreover, we can modify the inner and outer radii of the cross-section directly from the Dimensions panel. Now let's generate the mesh and check the default element size. I right-click on Mesh and select Generate Mesh. As you can see, the default element size is 5 mm, which is appropriate for this simulation. The beam cross-section is also visible in the graphics window. We can show or hide the cross-section view by going to the Display tab and clicking on Thick Shells and Beams. As you can see, the cross-section disappears. I enable it again. Now it's time to define the boundary conditions. First, a compressive force is applied at the top of the beam. I right-click on Static Structural and select Force. I change the selection filter to Vertex, select the top vertex of the beam, and click Apply. Then I change the definition to Components and specify -1 Newton and press Enter. Note that the magnitude of the force is not important because the load multiplier determines the critical buckling force. Next, we need to restrain the beam in the X direction. I right-click on Static Structural and select Displacement. I select the top vertex, click Apply, and set the X displacement to 0. Now the beam cannot move in the X direction. I want to analyze buckling in the XY plane, so I must also restrain motion in the Z direction. I right-click on Static Structural and select Displacement again. I switch to the Edge selection filter, select the beam edge, and click Apply. Then I set the Z displacement to 0 and press Enter. Now buckling is constrained to occur in the XY plane. Finally, I fix the bottom of the beam. I right-click on Static Structural, select Fixed Support, switch to the Vertex filter, select the bottom vertex of the beam, and click Apply. The boundary conditions are now correctly defined. Now we can solve the model. I right-click on Static Structural and select Solve. The solution is completed without any warnings. Now let's check the displacement results. I right-click on Solution and select Total Deformation from the Insert menu. Then I right-click Total Deformation and select Evaluate All Results. Here is the deformation result. Let's play the animation to observe the deformation behavior. As shown in the animation, the beam only compresses in the Y direction. This completes the first step of the buckling analysis. Now I close the ANSYS mechanical window. Next, it's time to add the Eigenvalue Buckling analysis. In ANSYS Workbench, I drag the Eigenvalue Buckling system and drop it onto the solution cell of the Static Structural system. As shown by the connection lines, all required information is shared with the Eigenvalue Buckling analysis. I double-click on the Setup cell of Eigenvalue Buckling. Before solving, the Static Structural analysis must be updated, so I right-click on Static Structural and select Solve. The solution is completed successfully. The Eigenvalue Buckling analysis does not require any additional boundary conditions or options. We only need to solve it. If I right-click on Eigenvalue Buckling, there are no options to define boundary conditions. I right-click on Eigenvalue Buckling and select Solve. The solution is complete. Now, let's view the buckling mode shapes. I click on the Solution B6 node, then right-click on the first mode in the tabular data and select Create Mode Shape Result. Next, I right-click on Total Deformation and choose Evaluate All Results. Here is the first buckling mode shape. The load multiplier represents a factor that multiplies the applied reference load of 1 Newton to give the critical buckling force. This means that when the applied load reaches this value, the beam will buckle. If we change the applied force, for example to 2 newtons or 3 newtons instead of 1 newton, the load multiplier will be divided by 2 or 3 respectively. This brings us to the end of the tutorial. Thank you for watching.